Hey, it's Masaki from Danza Competitive Programming Club, and I'm going to be talking about binary search and Meguru-style binary search. So this is mainly adapted from this Japanese article right here, so it's going to be linked. So how does binary search work? Let's say you have an array of sorted numbers like this. How do you check whether a value is in that array? So a basic approach might be linear search. So look at every single index and check whether or not that number is in the array. And that's going to take order of n time because in the worst case scenario, you're going to have to look through every single index, right? But with binary search, you can select the middle index and then compare it with the value, the key value that you're searching for, and that's going to cut the total search space in half. You can repeatedly have the total search space in order to process this in log of n time. So let's say you have this array here, you can check the middle, and let's say we're looking for 23. So 16 is less than 23, which means that this entire region here, from index 0 to index 3, all these numbers necessarily cannot be greater than or equal to 23 because this is a sorted array. So you can cut the search space in half and keep on repeatedly doing that. So sample code might be something like this, where you have left is equal to 0, right is equal to, well, commonly n minus 1 or something, array.size minus 1, and then while right is greater than or equal to left, you take the average. So this is just a fancy way of writing left plus right divided by 2, except ensuring that you won't get overflow. And then you're checking if that value in the middle is equal to the key value that you're looking for. In that case, return that middle value, the middle index, and then else you'd shift the right over to the middle, or you'd shift the left over to the middle. So what that looks like is, so you find 4, and then you know that this is too small. So the left side needs to move up. So you have a left pointer and a right pointer, just like a counter that counts the index. And then, so if it's too small, the left moves up. And then if it's too large, like the second middle point that the algorithm was selected, then you move the right side down. So that's all this is doing. And a more generalized form is in the C++ standard library called lower bound. So how this works is it returns an iterator pointing to the first element in the range from first to last, not including last, which does not compare less than the value. So let's say you call lower bound on this array here. So maybe a vector. And you have the vector.begin, vector.end, and then you have the value that you're searching for. And then the lower bound, if you search for 20, if you have the value, it's going to return the same position, because that's going to be the lowest index where the array of index is greater than or equal to the key. And you also get, whenever there are multiple of the key values, you're going to get the lowest one. So if you remember the first algorithm that we checked, the middle value, let's say you look for 20 first in this index and index 2, then it would return 2. Instead, the lower bound is going to get the lowest one. So you get extra information. Let's say the value is not in the array. So in this case, lower bound is going to return 1, the index of this 21 value, because that's going to be the lowest index where array of index is greater than or equal to the key. And in the case where none of these values are greater than or equal to the key, it's going to return the array, the vector.end kind of pointer. So some benefits of the lower bound is that even if the value isn't in there, you can know how many values in the array are smaller or larger than the value that you searched. And if there are multiple of the target values, you can find the smallest occurrence. And you can combine it with something called upper bound in order to find out how many of the target value exists. And then upper bound, just quickly, is going to return the first element in the range first to last, which compares greater than the value. So the array of index is greater than, not including the target key. So let's say you have this right here. Upper bound is going to return this index value or this index pointer or something like that. So yeah, so you have 0, 1, 2, 3, 4. So it's going to return 4 or the pointer to right here. Iterator. And then a more generalized binary search, kind of like this, the upper bound and lower bound is, you can represent it kind of like this. And let's say the pink region shows where the array of index is going to be larger than equal to the target. So you're always going to have this region where everything to the right is going to be greater than or equal to the target, and then everything to the left is going to be less than the target. And then we want to return this value right here, which is greater than or equal to the target, but the lowest value. So this is what we're looking for. And so in the final state, we end up with something like this, where the left position is right here, the right position is right here, and the difference between these two is going to become 1. And so you can rewrite this lower bound as something like this, where you have left is equal to -1, right is equal to array.size, and I'll explain that in a second, but right minus left is greater than or greater than 1, and then at the end it will return right. So it'll end when these two are next to each other, and then it'll return that right value. So the reason why left starts at -1 and right starts at n is because, let's say all the values in the array are greater than or equal to the target. Then -1, and that means that 0 is going to return true, and all the values in array of left must be less than the target. So we have to get it out of the bounds, and then for the right side, if all the values in the array are going to be less than the target, that would mean that left has to go to n-1 or array.size -1, and then right would be at n. So that's why we set it to -1 and array.size. And then you can generalize this further, and this is called Meguru-style binary search specifically, where you put one part as okay and one part as bad or not good, and then you can set the absolute value of the okay region minus the not good region, and work off of it like that. And that makes it even more generalized. So you take the average like before, and here you can't do the same trick with left plus right minus left over 2, because you don't know whether the okay value is going to be smaller or the not good value is going to be smaller. This is going to work in either case, but you return if is okay, and you have this helper function, then you set the okay part to the middle, and then else set the not good part to the middle, and return okay. So this makes it really, really simple. So if you show it here, so this pink region is going to be the okay region, and then this white region here is going to be the not good region, and you can define it kind of like that. You can also do the opposite thing, right, where you set okay to start from -1, and then not good to start from the right side, and that would work as well in this generalized form. So that's why you might want to try the absolute value one. I actually in practice find it easier to just do left and right and do this implementation. So yeah, this is worth trying out, and this as well, this form with the 1 greater than 1, I think this is really helpful, and defining it as this entire region to the right works, this entire region to the left doesn't work, or vice versa, and then just really thinking about left and right ending up next to each other, which one should return true, which one should return false. If you can get that working, then I don't think you're gonna mess up binary search. So that's the entire point of this version of the binary search in comparison to the first version, where you get very, very limited information. It's going to return -1. What does that mean, right? Like, does the value doesn't exist, but is it too big? Is it too small? You don't get a lot of information. So there are a lot of limitations to the regular version, and it's also harder to implement a lot of the time because you have to put the -1s and +1s and things like that. And you can even use binary search on floating point values. So let's say you're trying to find the square root of a number, like square root of 2. You can actually do binary search on the square root of a number and get really, really good precision. So let's say you're trying to find 10 to the -6 precision. And you can pass that in, and you can do while OK minus bad is greater than the precision. And then take the average middle like before. Make sure you're using doubles, of course. And then in this check part, you can also have a helper function, but in this check part you can write if the middle value times the middle value is greater than or equal to the number, then set the OK value to middle. So you're trying to find the square root. You take a random guess, and if that value is too big, then you shift the right side down. If the value is too small, then you shift the left side up. So you're doing the exact same thing as binary search. You're doing a binary search on floating point numbers and setting it equal to the precision and stuff like that. So you can actually do binary search on like square root and stuff like that. So very, very useful to know. And then as a bonus, who is Meguru? What is this Meguru-style binary search? It's a parody impersonation Twitter account for a visual novel character that does competitive programming. Like, not within the story, but they just made them do competitive programming just as a joke. And so a lot of competitive programmers refer to this, Japanese competitive programmers refer to this as Meguru-style binary search. And so you can find a translation to their Twitter post where they discuss binary search. And so this is a post that mentions the absolute value of OK minus not good. And yeah, so you can see that in the presentation. And then I'm gonna do one sample problem. This is probably the lowest difficulty binary search problem that I could find. So maybe pause and try to solve it yourself with this information, and maybe come back afterwards. Okay. So to explain the premise of this problem, you have two lists of numbers, each list having length of n. Each number in one list has a corresponding number in the other list. The correspondence is that if both lists were sorted and placed side by side, each pair of numbers would correspond. For example, in list 48, 10, 97 and 7, 46, 20, the corresponding numbers are 10 with 7, 48 with 20, 97 with 46. So, and you want to keep the lists synchronized, but you know that the second list has gotten out of order. You want to put them in the same order as the first list according to the correspondences. So basically, you have this original order, and then the second list has gone out of order, and the original order, I guess they're synchronized and you're shifting them in the same pattern, but the second one got messed up. So what you have to do is keep one copy of the original one, and then sort these two individual lists, and then you'll find correspondences, and going through that original list that wasn't sorted, find the index that corresponds to this. So this will be 0, 1, 2, and then find the index that corresponds, the number that corresponds with the index in that unsorted list for the second one. And you can do this with binary search by like searching for a number. So I don't start writing code first. Input contains at most 100 test cases. You start with a number, so you're not given the number of test cases total. So int n, while you can just make it an infinite loop, input in n, and then if n is equal to 0, break, or return, or whatever. And then you get 2 n lines. First n lines are the first list, second n lines are the second list. So let's make list 1 of size n and list 2 of size n. And then I also want a list 1 copy as well. This is just a short way to input in the numbers. So pass by reference. So I'm just reading in n numbers, reading in n numbers. And then list 1 copy is equal to list 1. And then I want to sort list 1 dot begin, list 1 dot end, sort list 2 dot begin, list 2 dot end. Some people use have shorthands for begin and end, like this entire sequence. But and then going through every number in the copy, which is not sorted, I want to binary search it in the first list, and then so that will get me, for example, let's say I search for 48 in the first list, so that's going to be the second one if it was sorted, right? Like index 1, and then I want to find index 1 in the sorted list in the second one. So I want to find the index in the sorted list for the unsorted one. So I is going to be the unsorted value, and then I want to find that unsorted value in the sorted list. And then int index is equal to, and you can, so first I'll show lower bound, and then I'll also implement the binary search as well. So list 1 is the sorted list, and I'm searching for I, and you can find the index value by doing lower bound minus list 1 dot begin. So you're given an iterator by using lower bound, and if you subtract the beginning iterator, then you get the difference in the iterators, and that's going to be equal to the index. So it's a nice trick to know. And then I want to find the list 2 index, and I guess I just print it out. So output list 2 of index, and then I'm gonna do new line, new line. So this actually, I think this actually works, and this will already pass, I think. And so this is very, very quick. Lower bound is really great, but let me implement this lower bound as well. Lower of, let's pass in, let's pass in list 1 and the value, right? I comma list 1, and then I want to get the index value that corresponds with it. So int lower of int target and vector int pass by reference list, and then you can, I guess you can do okay and bad. Yeah, let's just do the way. So okay, let's do in the conditional statement, I'll find, there are no duplicates and stuff like that, so you don't really have to do anything, but int target vector int list. If no, this is going to be the middle value, right? I'm going to pass in the middle value, and if the list of middle value and target is greater than or equal to the target, and return true, return false. So if I want it greater than or equal to the target, then that means if I have a really, really large value in a sorted list, then I want to be returning true. So OK is going to be on the right side. So that might be list.size. And then bad is going to equal -1. And while OK is larger, it's greater than 1. Int mid is equal to OK plus bad divided by 2. And I don't think we need to worry about overflow for this problem. List size is 5,000 at max. So that's going to be 5,000, and then the largest value here, OK plus bad, is going to be 5,000 plus 5,000. Yeah, so that's not going to overflow, so don't need to worry about that. And then if is OK int mid, and then target, and then list, OK is equal to middle, else bad is equal to middle, and then return OK. And that should work. So this is the exact same thing as lower bound. And that's a demonstration of doing binary search. So, so just to explain one more time, so we're trying to find we're trying to find the index of random numbers. So let's say 48, you need to find 48 within the sorted list. So something like that. So you have the sorted list, and then you need to find, and then you have sorted list 2, and you need to find the thing that corresponds, right? And you have the unsorted list, or not really number line, but you have the unsorted list, and then that's gonna be, you have like random numbers, and then so you need to output random ones, and you need to find it. So you get random numbers, and then you search for it in that sorted list, and then find the corresponding value. So sort 1, sort 2, and then find corresponding values. So code would look something like this. And I'll just try submitting this one more time. Okay, let's just see that it works. Yeah, okay. So this you can do with any kind of binary search, so I think it should be relatively easy, and even if you mess up a little bit, it might still pass and things like that. But yeah, maybe check out some of these two problems. Might be a little bit trickier. You have to do a different subproblem to give a hint. You have to modify the isOK function, so you have to do a little bit more in the middle part, and it also the questions are a lot easier if you know that it's binary search, so there's things to watch out for. Okay, thanks for watching.